Good to have you back for the second part of 8.6 solving logarithmic equations. We solved exponential equations in part 1, and today you're going to like the log equations because they're pretty easy and they can be fun at times. I used the word fun. When this lesson on solving logarithmic equations is complete, you'll know how to solve these equations by using your rewrite skills, by using your condensing skills. We'll also be looking for extraneous solutions once again. We've done that before. And we are going to see what it means to have a logarithmic equation that is undefined. Solving logarithmic equations, we have example 1 here. Log base 3 of 5x minus 1 equals log base 3 of x plus 7. Now you'll notice that I have a log on one side of the equation and a log on the other side of the equation. And that's good news for us because what we can do there is we can technically take both sides of the equation and divide by log base 3. And the reason why I'm able to do that is because if you really look at this carefully, this is actually one single monomial term. So that allows me to divide by log base 3, and whatever I do to one side, I do to the other because this other side on the right is also a single monomial term. This is all multiplication going on here, log base 3 of x plus 7, and that's why it's a monomial. That's great because the logs drop out of the problem, and I'm left with a simple 5x minus 1 equals x plus 7 equation. Using our Algebra 1 skill, we get 4x equals 8. Dividing by 4, x equals 2, and that is our final answer. So just to recap something you'll want to get in your notes, a single log on each side of the equation means that we're allowed to drop the logs. Now in our next example, where we have log base 5 of 3x plus 1 equals 2, you'll see that we have a single log on the left-hand side of the equation, and we don't have a log on the right-hand side. That means we have to incorporate a different skill for this problem. What skill is it? It's one that you're familiar with. I wonder if you figured it out yet. I can simply do a rewrite here. So 5 to the second equals 3x plus 1. So I took the base of the log and I made it the base of the power, and I moved that power up to the base, so 5 squared, and slid 3x plus 1 to the other side. Simply complete the process of solving the equation now, and we will get 24 equals 3x, dividing by 3, x equals 8. That is our final answer. So what did we learn in this particular example? We learned that if you have a single log on one side of the equation, do a rewrite. Before we get started on this next example, you're going to need your calculator. So if you don't have it with you, press that pause key, go ahead and find it, and come on back. For those of you ready to go, in example 3, we have ln times the x plus 3 minus 2 equals 8. To solve this problem, the first step you want to do is to get the ln term alone. So let's go ahead and take that negative 2 and add it to both sides, and we get ln times x plus 3 equals 10. Then we're going to want to go ahead and replace that ln with log base e. We've done this before, so we're going to incorporate many different skills here. And now that I have that done, can you figure out what we need to do next? You guessed right if you think we have to do a rewrite. So e to the 10th equals x plus 3. Now go ahead and get the variable alone, and we get e to the 10th minus 3. Remember, it's not part of the power. And at this point, we have to go ahead and do some calculator work. So now that I've gone ahead and solved for x, my final step is to use the e key to calculate. And here's how that will look. If I go ahead and do the equation, which is e, and you're going to have to use your second key if you have the same type of calculator, to the 10th, and then subtract the 3, and we get 22,023.46579. That 7 will make the 5 go up to a 6. So our final answer is going to be x equals 22,023.466. In example 4 here, we have 12 ln of x equals 44. The first thing I want to do is I want to isolate the ln. To do that, I'm going to divide both sides by 12. When I have both sides divided by 12, it leaves me with the ln of x alone, which is great. I'm heading in the right direction. And the 44 over 12 reduces to 11 over 3. Now what do I need to do? How about if I replace that ln with log base e of x? And that's going to set me up for what? I have on one side a single log. So that means I have only one option here, and that is to do a rewrite. So on this rewrite, I'm going to get e to the 11 thirds equals x. I've gotten x by itself, so I've solved, and now I simply have to do the calculation. A little bit tricky here because you just have to simply remember to take the exponent and use parentheses before you divide out that 3, close it out, and you will get an approximate answer of 39.121. That is our final answer. Well, we've been doing quite a few examples, so I thought, hey, let's get a little joke in here. I hope you like it. A man went to the rocket station and asked for a ticket to the moon. "Sorry, sir," said the attendant. "The moon is full just now." In this next example 5, we have an interesting one because we have 2 logs on the left and 1 log on the right. That means we have to do a little bit of work here. So of this log base 3 of 6 plus log base 3 of 8 equals log base 3 of x, the first thing we have to do is condense. So what does a plus sign mean? We remember that a plus sign means that we have to go ahead and make this multiplication. So I'm going to write log base 3, 6 times 8 equals log base 3 of x. So there I did. I condensed. And the next thing I want to do is to multiply this out. So log base 3 of 48 equals log base 3 of x. Now that I see that I have a single log on both sides, what am I going to do here? I'm going to drop those logs, and what am I left with? 48 equals x. That is my final answer. Okay, it's time for you to give one a try here. You've got a 2 log base 6 of 4 minus 1/3 log base 6 of 8 equals log base 6 of x. Give that one a try. Press that pause key. Come on back. I'll reveal the answer. Okay, so if you did this correctly and you applied your power rule along with your condensing rules, you got an answer of x equals 8. How'd you do? When it comes to logs, we have a situation where the element of a log function is negative, then it creates an undefined situation, and I'm going to show you just why that happens. If I have this log base 5 of negative 6, and I want to evaluate it, I'm going to set it to x, right? And when I do so, I'm going to do a rewrite. So I have 5 to some power results in a negative 6. Now think about that. Is there ever going to be a number that I can replace in this x such that it's going to result in a negative number? Well, you can think long and hard about that, but the answer to that is no, it's not going to happen. So therefore, if this particular number of the log is negative, it's going to result in an undefined situation, and I need to make sure you have that in your notes. So a negative number next to the log means that the whole log function just became undefined. Another example of that, let's take a look at something else. If I have an equation of log base 3 of 2x plus 3 equals log base 3 of x minus 4, and I go ahead and evaluate this equation and actually solve it, I'm going to drop the logs out, because if I have a single log on both sides, they drop out. We learned that earlier today. Then I'm left with 2x plus 3 equals x minus 4. I'm going to solve and get x equals negative 7. Now I don't know if it's going to be an undefined situation till I plug it back into here and see if it comes out negative. So I'm going to go ahead and plug this in and see what happens. So I have log of 3 times 2 times negative 7 plus 3, and see what happens here. And I'm going to get log of 3 times negative 14 plus 3, and here it is. I have a negative 11, and for that reason it's undefined. It doesn't matter which one I go back to. If I get a negative answer, it's undefined. So if I would have gone back up into this example up here, if I would have gone to this particular part of the problem and it became negative, which it did because the log base 3 of negative 7 minus 4 gives me also a negative 11. That's just a coincidence. They don't always come out to be the same number. If that happens, then it's also undefined. So either one, if either one's negative, it is undefined. Solving log equations with extraneous solutions is our last example. Remember that an extraneous solution means that when I get my answer, if I plug it back into the equation and it makes the equation false, I must eliminate it as a possible answer. So let's take a look at this log of 5x plus the log of x minus 1 equals 2. I see that I have a log on both sides of the equation, and since that happens, it means I'm going to condense, and I have plus sign there. So the plus sign means I'm going to multiply. So 5x times x minus 1 equals 2. Since I cannot go any further because I have a single log on one side, now you can see this one log on the left. If that's all that I have to do what we call a rewrite. But how do I know what to rewrite? I don't have a base. Well, remember that if you don't see a base by that log, it's understood to be a base of 10. So my rewrite's going to be 10 to the second equals the whole thing here, 5x times x minus 1. I think it's time for me to go ahead and evaluate what I have so far. So I have to take that 10 and square it to get 100. Distribute the 5x to the quantity, and that would give me 5x squared minus 5x. I'm going to get everything over to one side because I'm in a quadratic equation. That 2 told me that. So 0 equals 5x squared minus 5x plus minus 100. We're going to subtract that from both sides. And now, to make this problem a little bit easier, I'm going to take out the GCF. So I'm going to divide everything by 5. And that leaves me with 0 equals x squared minus x minus 20. Now once again, because I'm in a quadratic, I'm going to have to use my MAF skills. I'm going to do that for you, and I'm going to break it down, and it breaks down to an x minus 5, x plus 4. Setting both of those quantities to 0, I get x equals 5 and x equals a negative 4. Now, what I have to do here is I have to go back to the original equation, sub in both my answers to see if either one of them make an untrue equation. Okay, so I'm going to go ahead and take my first value, which is the 5, and see what happens. I have log 5 times 5 plus log 5 minus 1. Does that equal 2? Well, let me see. I have a log of 25 plus a log of 4 equals 2. And so I have log 25 times 4 equals 2. So log of 100 equals 2. And finally, I have a 10 squared equals 100. 100 equals 100. So that is true. The next one that I'm going to do is the negative 4. Log 5 times negative 4 plus log negative 4 minus 1. Does that equal 2? Well, right here, I know the problem is going to have to stop because that is a no solution right there. So I'm going to eliminate that x minus 4 because I got a negative for that number of the log. And so our final answer is that x equals 5. It's time for you to give it a try now. Take a look at this log base 2 of x plus the log base 2 of x minus 7 equals 3. Come on back when you're finished and we'll see how you did. Okay, so when you did this problem, you got two answers. You got x equals 8 and that x equals negative 1. You went back and checked that negative 1. It was extraneous. Final answer is x equals 8. I think you'll really like this wrap-up because we had a lot going on today. You probably want to make sure you have this in check. Single logs on both sides, drop the logs. Single log on one side, do a rewrite. More than one log on one side, condense. If you have a negative number next to the log, it's undefined. And always check for extraneous solutions. That's mostly when you're in a quadratic equation type problem. That's it for our log equations.